what its probabilities of measuring certain things, and what value does it take at a certain position at a certain time, and it's a state. So a state's a very general sort of concept in physics, right? So we're now looking on this state, if you like, as a vector. So we can just talk about a state vector, right? And we represent this state vector. In this case, if you're thinking wave functions, we can represent that as ket, right? So if you see this symbol here, now it's not a bra ket. Bra ket was shorthand for the overlap integral. So this is in a sense the right-hand side of the bra ket, and it's just called the ket. The bra is the part on the left-hand side, and the ket was the part on the right-hand side. So this is just called a ket. So instead of using this symbol here, the wave function symbol, psi, psi function, we'll just talk about a ket, and we'll represent that state instead of as using psi. We'll use the ket symbol, which is a vertical line and a right arrow, pointing to the right. And if you see that, you just say, oh, it's a ket. Okay, its label is ket, K-E-T. All right. Now you've seen that as the right-hand side of bra ket. Okay. So that means this left side here is also a kind of state. Don't worry about that. We'll get onto that more later. But if you see this here, so a vertical line and the left pointing arrow, those two together is called a bra, and a bra is also a kind of state. And when you put a bra and a ket together, you're talking about some kind of product, like a dot product, or the overlap integral. So a bra ket is some sort of product, but the ket alone is just the state. Okay, so this will be our new language from now on. So get used to it. Okay, all right. Now, don't confuse a ket, a state, with just an ordinary three-dimensional vector. Right? It's much more abstract than that, and it's just think of a ket as a quantum state. Right? For example, a psi function. Okay. Now, a couple of quasi-mathematical comments here. Almost sort of thrown in. So this to me is an example of physicists thinking. There's two. Well, when it comes to math physics, I like to think I'm as at home thinking pure math as a pure mathematician, as a mathematical physicist. But I definitely prefer the logical, top-down, step by logical step type reasoning of the pure mathematicians, because it's cleaner, it's sequential, it's logical. You're not jumping around the way math physicists tend to do. I like the greater rigor and the step-by-step logic of pure mathematicians. Anyway, so here's something that's thrown in a bit by a physicist. So he's just saying that if you have a basis, remember what a basis was? It's a set of vectors that from which, by weighting them and summing them, you can create any vector in the vector space that you're talking about. Like, for example, if we're talking about just ordinary three-dimensional space, your basis would be these three unit vectors with the hat over them. Now, in a couple of sessions, I will use this hat in a completely different context. So don't be confused. In this context, talking about unit vectors, the little hat here, like the symbol, just says that this vector has unit length. So these three unit vectors, they form a basis, like a foundation, because you can form by creating a weighted sum. So I can form any three-dimensional vector in that three-dimensional space by using these three unit vectors. So these three form a basis. They allow you to, they're the foundation. They allow you to form any vector v that you want. For example, if the coordinates of that vector, the tip of the arrow, if you like, at position x, y, z in Cartesian three-dimensional space, so your vector v would then be x times this plus y times this plus z times this, right? And that x, y, z is quite general, so any vector v can be built up from, based on, hence basis, on these three vectors, right? Now, in the case of 3D, these three are complete in the sense you don't need any more. You do not need a fourth one, because you can form any vector v, general vector v, using these three. You don't need another one. These three are sufficient, right? They're enough to form any three-dimensional vector. Now, say I only had two of them. Say I only had the I and the j. So that would not be sufficient. That set then of ei and ej would not be complete, because I could create I could have vectors that I wanted to represent in terms of I, j, and k, but the k is missing. So so that set of I and j only would not be complete. Okay? So what this sentence here is saying effectively is that if you have a space, vector space of big N dimensions, right? So it's an n-dimensional space. Like, for example, in relativity, n might be 4, so you've got a four-dimensional space. If you're talking string theory, you might have an 11-dimensional space, right? So if you have a basis of that n-dimensional space, your basis requires n basis vectors. Okay? Otherwise it's not complete. If you don't have enough of these basis vectors, you can have vector v, which is now in n-dimensional space. You can have vectors that you cannot write as a weighted sum of your vectors unless there's enough of them. And how big is enough? Well, for an n-dimensional space, you need n of these basis vectors. Right? That's what that's saying. Now, things get a bit complicated when you go to infinite dimensional spaces, and that happens a lot in quantum mechanics. So the mathematics of infinite dimensional spaces, that's Hilbert Space, and that can get that's a whole specialty in its own right. Tends to be quite advanced, definitely graduate level. So at undergrad level we'll gloss over it a little bit, but just be conscious that when you're talking infinite dimensional spaces, Hilbert space, the concept of the dimension, what does a complete set of basis vectors? When you have an infinite dimensional space, that becomes, it gets a lot more subtle. So at undergrad level, just gloss over it a bit, right? But just keep in mind, it's not so straightforward, right? You need to get into the mathematics of Hilbert space theory and so forth. All right. Now I've got 2 bars here. In a sense, a new topic, but end of the session. we're going to talk about operators now in the context of quantum mechanics. Now I've talked a bit about operators when talking about eigen-equations. So you're sort of partly familiar with the idea of an operator. Remember, basically an operator is just some symbol that tells you to do something. Now in the context of quantum mechanics, an operator is something that changes a function. Like it can change a wave function into something else. It can change a ket, using our new language. It can change a ket into some other ket. Right? So an operator is a kind of mathematical changer. It changes a function into another function, or a ket into another ket. So think of it in those terms. Right? Now here's your STI. Your Schrödinger time-independent equation is STI here, and we've rewritten, instead of your usual Schrödinger equation in this form, minus h bar squared over 2m del is the three-dimensional form, so del squared plus v, okay, equals a discrete quantized allowed energy level E, so times your wave function again. Or we could write this as a ket. We could do this kind of thing, just another language. But have a look at this. This, I've said this before, but this is an eigenequation. Right? Here's an operator. In this case, it's this. Right? Here's your operator. You've got an eigenfunction both sides, and here's your eigenvalue. So the whole thing is an eigenequation. Okay. Now, this h hat, now, do not be confused, this hat here means it's a unit vector, it has length 1. This hat here, completely different in concept, except we're using the same symbol, but this hat here now tells you that this symbol h here is an operator, okay? So don't be confused. They're two quite different things. This hat here tells you that what is underneath it is an operator, right? And this operator operates on this wave function, just the function. So an operator changes a function into another function. Well, in this case, this function is in a sense the same direction, but it's now longer or shorter by this factor e. Okay. So this thing here, which is this, in fact, because it's got a hat over it, that means it's an operator, right? I've run out of board, but we'll continue on with this kind of thinking. We'll talk a lot more about operators in the next 2 sessions, a lot more.